In the next set of lectures, we're going to look at this freshly made filtrate that we've just squeezed out of the glomerulus, and we're going to follow it as it moves through the tubules in the nephron. Along the way, we're going to explore mostly reabsorption, but we'll look at a little bit of secretion as well. This particular lecture is just going to introduce you to some major concepts of reabsorption so that you have a good foundation to build upon when we explore how reabsorption happens in the various sections of the nephron. So in this lecture, we're going to address what is in filtrate when we start, what basically happens to that filtrate as it moves through the nephron in terms of volume and osmolarity. We'll look at the mechanics of reabsorption, and then we're going to take a look at some terminology associated with reabsorption. In subsequent videos, we are going to look at the details of reabsorption in specific segments of the nephron. So we'll do a whole lecture on reabsorption just in the proximal tubule and reabsorption just in the loop of Henle, etc. But for now, let's get started with introducing some basic concepts. So it would be helpful if we actually knew what was in filtrate so that we knew what was available for us to potentially reabsorb. So when filtrate is freshly squeezed, so there's my filtrate, and if I sample it, it's going to look a whole lot like plasma, actually, with one glaring exception. And that glaring exception is the plasma proteins. Remember that most of the plasma proteins are in fact retained in the blood. So I could potentially copy this list and move it over here, and I would have a list of filtrate. Now you do not need to copy all of this down. I simply wrote out a more extensive list so that you could see that there's actually a lot of different stuff in the plasma and therefore a lot of different stuff in the filtrate. And a lot of the stuff that is in the filtrate is in fact going to be reabsorbed. Now, I'm going to pick and choose my battles here and not cover everything on this list, but rather we're going to select a few solutes to follow and of course water. So what I mean is that in future lectures, we're only going to be looking at some of these things. We're not going to be looking at all of them. And that's simply in the interest of time. So water, of course, is going to be a big one to reabsorb, so we'll look at that. We'll also look at the dominant ions in the extracellular fluid, which is sodium and chloride. We are going to look at glucose as a stand-in for nutrients in general. Indeed, what happens to glucose also happens to amino acids and nucleic acids. And then we'll look at urea as an example of reabsorption of waste products. The osmolarity of plasma is approximately 290 milliosmoles. And what that means is that if filtrate is almost identical to plasma, then filtrate at this point is also 290 milliosmoles. Okay, let's take a look at what happens to filtrate as it moves through the nephron. So in my image here, I have an expanded nephron, and just very briefly, this is Bowman's capsule in the glomerulus, proximal tubule, descending loop of Henle, ascending loop of Henle, distal tubule, and collecting duct. I'm going to put a series of checkpoints, and on each checkpoint, we're going to take a look at how the filtrate has changed from the previous checkpoint. So I'm going to put one checkpoint there. I'll put another checkpoint as we leave the proximal tubule and enter the descending loop of Henle. I'll put another checkpoint at the bottom of the loop of Henle, and another one as we come back up to the and another one as we come back up towards the distal tubule, and then finally one down here as we leave the collecting duct and enter a minor calyx to become urine. So let's go ahead and start with filtrate at our first checkpoint. In a previous lecture, we learned about the glomerular filtration rate, and we know that the glomerular filtration rate should be maintained at 180 liters per day. So it would be reasonable to assume that the amount of filtrate that crosses our first checkpoint collectively across all of the nephrons and per day is going to be about 180 liters. And we just saw that the osmolarity of plasma and the osmolarity of filtrate at this point are about the same. So it would make sense that the osmolarity would also be about 290 milliosmoles. Now, quite a lot of reabsorption is going to occur in that proximal tubule, so that by the time we cross our next checkpoint, where the filtrate is leaving the proximal tubule and beginning its descent down the descending loop of Henle, a lot of the water has been reabsorbed. And in fact, the amount that crosses this checkpoint is about 54 liters per day. But the osmolarity is still 290. Now, at this point, why we've lost so much fluid, but the osmolarity is the same, will not be clear. That's going to be covered in the next lecture. I'm simply showing you that the filtrate volume and, as we're about to see, the osmolarity is going to change as that filtrate moves. So the filtrate, or what's left of it, is now going to move down the descending loop of Henle. By the time it reaches the very bottom, it's around 18 liters per day, with an osmolarity of approximately 1200 milliosmoles. That's way more concentrated than it was when it started the trip down. Then that fluid is going to come back up, and as it crosses over into the distal tubule, it's still about 18 liters per day, but it is about 100 milliosmoles. So now much more dilute. That filtrate is now going to enter this distal tubule and the collecting duct. Now, there's something different about the distal tubule and the collecting duct from the other tubules. The distal tubule and the collecting duct can actually alter or change how much reabsorption they do. And if they, let's just pick water for a moment. Let's say that you're going to reabsorb a lot of water. If the collecting duct decides to reabsorb a lot of water here, then there's not going to be very much water left over at the bottom. And so this is going to be reflected in your urine volume, because once you reach this last checkpoint, your urine, you don't get to be reabsorbed anymore. So we've changed the identity from filtrate to urine at that point, and there's no more modification to the fluid. So if you reabsorb a lot of water, then there's not a lot of volume left, and so you'll have a low volume and you won't urinate very much. But let's say instead you decide not to reabsorb very much water over here. Again, the distal tubule and the collecting duct can vary or alter how much reabsorption they do based on the body's needs. So let's say that you only reabsorb maybe just a little bit of water. Then by the end, you're going to have a lot more fluid. And so when you use the restroom, you're going to have a much greater urinary output or urinary volume. And so the amount of fluid that crosses the collecting duct is going to vary depending on your body's state. So typical amounts could be anywhere from half a liter per day to many liters per day. So let's just say 5 liters per day. Likewise, the osmolarity can also vary. And you've experienced this with dilute versus concentrated urine. Dilute urine has a very low osmolarity, maybe only 50 milliosmoles. Concentrated urine might approach 1200 milliosmoles. So think about scenarios where you produce a lot of urine that is also very dilute. Right, drinking a lot of water. If you drink a lot of water, then don't you urinate a lot and it tends to be pretty clear? Now think about when you're really dehydrated. When you're really dehydrated, are you urinating a lot? No. You're producing less urine and it tends to be more concentrated or a higher osmolarity. The processes, the feedback loops, the mechanisms by which the body receives signals and then adjusts the urinary composition is going to be a topic for a future lecture. But I just wanted to point out that the distal tubule here and the collecting duct do not reabsorb the same way all the time. Okay, let's take a look at the mechanisms by which reabsorption happens. In other words, what is reabsorption? What's actually happening at the cellular level that allows us to do reabsorption? So remember when I spent all that time on transepithelial transport and it probably felt like overkill then? Well, the reason I spent so much time on it was because I knew it was going to come back here. So transepithelial transport is required to reabsorb fluids. In fact, the process of reabsorption is a multifaceted process. So let us say that I have some substance X that is in my filtrate and I want to reabsorb it. What do I need to do? Well, the first thing I need to do is I need to actually move it into one of these epithelial cells here. So again, these are tight junctions. You might notice the tight junctions there, which means you're not going to slip through the cracks. You actually have to cross the membrane. So we are going to cross the apical membrane first. And then from here, we're going to need to cross the basolateral membrane. So we need to first cross the apical membrane. Then we're going to cross the basolateral membrane. And now we've effectively been recaptured by the body. So we've been reabsorbed. If fluid didn't move from here, it would just accumulate in the interstitial fluid and your kidneys would get really swollen and show edema, and that would be bad. So we need to remove this fluid. It turns out that the hydrostatic pressure in the peritubular capillary is very low, such that a large pressure gradient exists between the ISF and the peritubular capillary, which means that as things get reabsorbed into this interstitial fluid, it kind of gets vacuumed into the plasma of the peritubular capillary and then taken away from the kidneys. So you can think of that peritubular capillary as having kind of like a weak suction where it's just kind of constantly sucking whatever interstitial fluid is being produced by reabsorption. For our purposes, I don't really consider this. To me, it is enough if you have achieved these two steps. You've crossed the apical membrane and you've crossed the basolateral membrane. Now, remember that transepithelial transport is probably going to cost at least some type of energy. So it's not going to be free in every case. That said, the kidney is a very energetically expensive organ because it is doing a lot of this transepithelial transport, so much. So to optimally achieve as much transepithelial transport as possible without spending extra money, it is going to want to do as many things for free as it can. So now let's turn and take a look at passive versus active transport. Please take a good look at this image, pause if you need to, and then answer this quiz question. Is this active or passive reabsorption? Remember that if we pay for something at either end, either the apical membrane, which would be here, or the basolateral membrane, which is here, it's active. You have to pay for it somewhere along its journey. In this case, sodium reabsorption comes in through a channel protein, but is kicked out actively using primary active transport with the sodium-potassium pump. So this is going to be active reabsorption because you are paying for it on one side. It turns out that the sodium-potassium pump is going to be a major player in reabsorption. In fact, basically all of our setup for this particular process of reabsorption is going to be driven by that sodium-potassium pump. So there's a couple sayings in physiology that are related to renal physiology. And one of them is sodium drives everything. It's such an important saying, I'm actually going to put it down, even though it won't make a lot of sense right now. So the active reabsorption of sodium, or paying for sodium reabsorption, is going to set up a scenario that allows us to do some passive reabsorption of a lot of other stuff. And so in other words, you're paying for this, and then you get a bunch of free solutes and solvents that kind of hitch a ride on that. And so it's a lot like saying if you buy one, you get 4 for free. So if you think about it that way, you pay for sodium and then other stuff jumps on passively because of sodium's active transport. And at the heart of sodium's active transport is the sodium-potassium pump. So a subsequent saying is that the sodium-potassium pump drives everything, which is also true. So we'll see both of those in a lot more detail in the next lecture. The last thing that I want to talk about is looking at some terminology associated with reabsorption. For my lecture, I tend not to go into these in great detail, but I did want you to be aware of the terminology because they do cover some important nuance. So the first thing I would like you to do is take a look at this. Don't write any of it down. You'll notice that some of these are going to be things that we also highlighted in the first slide. These are going to be solutes or solvents that I'm going to be following as we go through the story of reabsorption. Like what happens to water, what happens to sodium, what happens to chloride. Now I want you to look at how much is reabsorbed, what percentage is reabsorbed. 99% of water is reabsorbed. 99.5% of sodium is reabsorbed. What? Wow, really? We tend to think of salt as a bad thing, but here we're like, no, we want to keep it. 100% of glucose is reabsorbed. 50% of urea is reabsorbed, and that's a waste product, but none of phenol is, which is another waste product. Strange. So clearly there's some selective reabsorption going on. Selective reabsorption means that you are picking and choosing what you want to reabsorb and not reabsorbing everything. So here we are selectively reabsorbing water, sodium, glucose, even urea, but not phenol. So selective reabsorption can be defined as you're selecting certain solutes to be reabsorbed. This is a general theme for the kidney. You don't reabsorb everything indiscriminately. You definitely have some priorities about what you want to reabsorb and other things you'll never reabsorb, like phenol. Obligatory reabsorption is the concept of reabsorbing something without deviation. In other words, like an action potential, it runs the same way every time. Filtrate passes through a part of that nephron, and you're going to reabsorb 20% of sodium that you see every time. So you are obligated to reabsorb something some way every time. Facultative reabsorption is where you kind of pick and choose, and facultative reabsorption usually refers to reabsorption that you alter or vary depending on the body's needs, and it is usually under the control of hormones. So obligatory reabsorption, you are obligated to reabsorb it this way, all the time, happens in the proximal tubule and the loop of Henle. We can think of this as autopilot reabsorption. We don't change it. Where facultative reabsorption is going to be reabsorption that you can vary. Do I want 10% of that sodium or do I want 30% of that sodium? Depending on your body's needs, which again is going to be coordinated through the use of hormones. This happens in the distal tubule and the collecting duct. Total reabsorption refers to the idea that you're reabsorbing something 100%. In our example, glucose is totally reabsorbed. So total reabsorption refers to 100%, or it should be 100% reabsorption. Only certain substances are totally reabsorbed. Glucose is one of them, or at least it should be one of them, which means there should be no glucose in your urine because it all should be reabsorbed. Okay, that concludes this part of the lecture. In our next lecture, we're going to dive into reabsorption in the proximal tubule and take a look at how sodium and the sodium-potassium pump drives it all. I'll see you in the next lecture.